In 1687, a book was published that, at first glance, seemed like just another academic work. A Latin tome filled with mathematical symbols and complex theories. But this book, published by the British mathematician Isaac Newton, would go on to change humanity's understanding of the universe forever. It wasn't about war, conquest, or the overthrow of kings. It was about a revolution that unfolded across the stars. Before Newton's groundbreaking work, the world was fragmented. Earth and the heavens seemed like two different realms. The fall of an apple was something that happened on the ground, while the planets and stars moved in ways that seemed disconnected from earthly experience. For centuries, humans accepted that the heavens had their own rules, divine and mysterious, beyond human understanding. The movement of the planets, the orbit of the moon, and the behavior of stars were seen as divine mysteries, separate from the predictable laws governing the Earth. And then Isaac Newton stepped in. Today, most people associate Newton with the story of an apple falling from a tree and hitting his head, leading to the discovery of gravity. But that story, while charming, barely scratches the surface of what Newton truly accomplished. The question he was really trying to answer was much bigger and more profound. Why does an apple fall to the ground, but the moon doesn't fall into the earth? This was the real mystery Newton sought to solve. Newton's mind was focused on understanding why objects on Earth fall due to gravity, but celestial bodies, like the moon, seem to defy this force. Why do the planets revolve around the sun without falling into it? Why does the moon stay in orbit? Why do the tides rise and fall? Before Newton, astronomers like Copernicus, Kepler, and Galileo had made huge strides in understanding the cosmos. Copernicus proposed a sun-centered solar system, Kepler formulated the laws of planetary motion, and Galileo championed the scientific method. Yet, they were all missing the final piece of the puzzle, the force that could explain why planets move the way they do. Newton wasn't the first to notice the laws of motion or gravity. Many had theorized about forces and motions in the heavens. However, Newton was the one who brought it all together, mathematically, and unified the ideas into one grand framework. This was the birth of modern physics. In 1684, Newton was approached by the astronomer Edmund Halley, yes, the same Halley who would later give his name to Halley's Comet. Halley had a question for Newton. If an object is influenced by a force that decreases with the square of the distance, what kind of orbit would it trace? This was not just a random question. It was the key to understanding the orbits of planets. Halley was looking for an answer, and Newton, in typical fashion, answered it without hesitation. The result was revolutionary. Newton's answer: an elliptical orbit. This was the same result that Kepler had observed for the planets, but Newton was the first to explain why this happened. Halley, stunned by the simplicity and power of Newton's answer, encouraged him to publish his findings. Halley even went so far as to fund Newton's work, personally covering the cost of the publication of Newton's Philosophia Naturalis Principia Mathematica, a book that would shake the very foundations of science. But even the publication of Principia wasn't smooth sailing. It wasn't just the ideas that caused controversy. There were personal battles too. The first major conflict came with the scientist Robert Hooke. Hooke, a contemporary of Newton, claimed that he had come up with the idea of the inverse square law of gravity before Newton. This claim created a public dispute over who had priority in the discovery of the law that would dominate physics for centuries. Newton, known for his pride and meticulous nature, was furious, and the rivalry between them escalated. But Newton was not only fighting with Hooke. The publication of Principia was also delayed because the Royal Society, which was supposed to fund its printing, had already exhausted its funds on another project, this one about fish. That's right, Newton's universe-altering work almost didn't see the light of day because of an expensive fish book. This unexpected obstacle was resolved only after Halley stepped in once again to fund the printing out of his own pocket. This sequence of events is often forgotten in the popular narrative of Newton as a solitary genius. In reality, Principia was not only the result of Newton's groundbreaking work, but also a series of fortunate and sometimes unfortunate circumstances that made the publication of the book possible. And when Principia was finally published, it did more than explain why an apple falls to the ground. It explained the very mechanics of the universe. Newton's theory unified the motions of the planets with the behavior of falling objects on Earth, proving that the same laws governed both. This was nothing short of revolutionary. For the first time in history, the heavens were governed by the same laws as the Earth. Newton's work did not just confirm the heliocentric model proposed by Copernicus, it gave it a physical explanation, a reason for why the planets revolve around the Sun. This was not just a scientific breakthrough, it was a shift in the way humans viewed the universe. Newton's work proved that the universe could be understood, not as a mysterious and unpredictable realm, but as a machine governed by natural laws. The universe was no longer a divine and unknowable place. It was a place that could be calculated, predicted, and understood through mathematics. Yet, as groundbreaking as Newton's work was, it was also not without its critics. Many in the scientific community, including prominent philosophers and mathematicians, could not accept the idea that an invisible force could act over vast distances, an idea that seemed too magical for many. Even Newton himself was uncomfortable with the idea of gravity acting over such distances without a known medium. However, despite the skepticism, the predictive power of Newton's laws could not be ignored. The laws he established were not just theoretical, they could be tested and verified. For example, Halley used Newton's calculations to predict the return of the famous comet that would later bear his name. 200 years later, when Albert Einstein came along with his theory of relativity, it didn't invalidate Newton's laws, it expanded them. Newton's laws remained the foundation of classical mechanics, still applicable to most everyday phenomena. But Einstein showed us that in extreme conditions, such as near massive objects like stars, Newton's laws no longer applied in the same way. But Newton's contribution was far more than just a theory about gravity. What he achieved with Principia was the birth of a new way of thinking about the world. The work did not just unify our understanding of the cosmos, it provided the tools for a new kind of knowledge, one that relied on observation, experimentation, and mathematical reasoning. So, Newton didn't just answer why an apple falls. He showed us that the same rules that govern falling apples also govern the stars, the planets, and everything in between. In the end, Newton didn't just change the world of science, he changed the way humans understood their place in the universe. For that, he will forever be remembered as one of the greatest thinkers in human history. Thanks for watching. Be sure to like, subscribe, and ring the bell for more incredible stories from history.